morning, everyone. Can you hear me?
Yeah.
Is that fine? Good. First of all, I would like to thank Wonderland AI for having me today, and thank you all guys coming to this session. So I'm very happy to share my latest research work in 3D scene understanding. Today, my talk is about learning to reconstruct and segment 3D scenes. First of all, let's look at today's AI systems. This demo shows the latest work is able to detect, segment, and recognize individual objects in pixel level on 2D images. You can see that the results are exciting. However, these systems are unable to perceive the 3D world. Basically, they don't understand the depth and also the 3D shape of all the objects like cars, people, right? However, our world is a complex collection of 3D objects instead of 2D pixels. It looks weird. So we believe that the future AI systems should be able to understand the 3D world like we human beings. There are a wide range of applications. For example, the robot grasping, navigation, autonomous driving, and also the augmented reality-based applications. Right. So today's talk, we are gonna purely focus on 3D scene understanding. We are going to talk about 3 pieces of our recent work. The first one is 3D scene reconstruction from 2D images. The second one is 3D instance segmentation. Basically, is to identify individual objects from large-scale 3D point clouds. The third part is about 3D semantic segmentation of super large point clouds, which will be talked by my colleague Qingyong. Right. Let's first look at this scene reconstruction. This is a very classic problem in academia and also in industry. So the problem is, how can we obtain the 3D shape from a couple of 2D images? The existing work, they usually recover the 3D voxel grids, triangle meshes, and also the point clouds. However, all these works have 3 limitations. The first one, these 3D representations are sparse and discrete. So they are unable to deliver fine-grained geometric details. The second is all these pipelines, these bedworks require 3D ground truth data to supervise. But it's super difficult to annotate the ground truth 3D shape because it's super difficult to obtain those shapes, right? And it's very costly. The third limitation is all of these approaches, primarily they just focus on simple objects. It's very hard to scale to like complex scenes, like our daily scenes, right? Which have multiple objects and there are visual occlusions, etc. So ideally, we could build a system that is able to recover smooth and continuous surface like the real world. And at the same time, when we train this system, we don't need 3D data. We just need like 2D images. That's enough. But of course, that's difficult. The third one is ideally our system is able to deal with individual objects as well as complex 3D scenes. That's an ideal case. Now we are gonna deliver you an ideal case. This is our latest work. We call it GRF. So fundamentally, we formulate the problem of a 3D scene reconstruction as a continuous neural function. This function takes a set of 2D images, which we can, captured from my mobile phone or any other like cameras. And then we learn features for every point in 3D space. And then we reproject that point into 2D space using 2D images to supervise this network. And then our 3D shape can be learned without 3D ground truth data. So here, the highlights is our method is, models the 3D scene as a continuous 3D representation. And also it only leads 2D images for separation. Of course, our formulation does not care about the content of the scene, whether it is object or complex scenes. Right, simple enough. So our approach, we tested it on like the complex synthetic data and also the real world complicated data sets. So far, our approach is the state of the art compared with all the latest approaches. This paper is just online like 2 weeks ago. So here I show some qualitative results of our approach. We can see that our approach is the second column. And the third column is the ground truth images, right? So all the details can be well recovered. The previous approaches have many artifacts. So here is a demo for synthetic dataset. These images and this 3D shape are recovered by our approach. It's amazing, isn't it? It looks very photorealistic. This is a result of our approach on real-world datasets. All these images are captured from our mobile phones. And then we just captured like a couple of images. And then our approach is able to recover all the shape and appearance from any view angles. Yeah, it looks very, very, photorealistic. Right. Now we can recover the 3D shape from 2D images. But sometimes we have Keynote, which is able to directly capture 3D shape directly. But the machine does not understand, okay, the type of the objects or the category or which one, the location of the categories. So here we are gonna present our work about instance segmentation. Basically, it's about giving a 30-point cloud. How can we identify individual objects from these point clouds, like 2D, like the instance segmentation in 2D images? Right, the existing approaches, once again, they have lots of limitations. For example, the proposal fail or proposal-based approaches, they are very heavy, post-processing steps. They have, and then also they have low object lists and requires multiple training stages. But our approach is very simple. Again, we just formulated as a two-stage, like two components. One component is to draw a large box, like a rough box for every object. And then we just focus on each object and then identify the individual objects, the foreground, the background, and then that's it. We don't have like a heavy computation, like heavy post-processing, and we have very high object list for every object. Right. So this is the detail of the first component, like the object detection. But we just ignore the details. If you have interest into the details, feel free to drop me an email for the details. Right. This is also about how can we mix network to learn the object bounding boxes. This is the given the learned bounding boxes, how can we identify the point clouds, the individual objects? All right, once again, this is a quantitative results of our approach on the standard scanlet datasets. At the time of our publication, we are the best approach, but now many other approaches better also build on our approach. Yeah. Here is the qualitative results, how our approach to first identify the object bounding boxes, and then segment each object in per point level. Right, here is a demo to show that our approach on the scanning dataset and also the S3D IS dataset. So it can be seen that for the indoor dataset, all the individual chairs and tables, like table 1, chair 1, can be precisely identified. We not only identify the individual objects, but we all at the same time we also recognize it. Okay, this is table 1, table 2, chair 1, chair 2. And also the other, like for example, the Chinese case, like the conference room, there are lots of similar objects, but still our approach can give, obtain very good results. We believe that this approach is able to, inspire many industry applications like augmented reality or, navigation or scene editing, lots of applications. Yeah. So that's all of my 2 pieces of work. And now my colleague Qingyong are going to talk about his exciting work on large-scale semantic segmentation. Thank you.
Thank you, Bo. Over to you, Qingyong.
Hello, can you hear me?
Yes, perfectly. Welcome and good morning.
Yeah, thank you for the invitation. And hello, everyone. I'm Qingyong, a second-year PhD student at the University of Oxford. So it's my pleasure to share my research with you. Yeah. Okay, so first I will introduce our Wonderland, and this is working aim to achieve the semantic segmentation of large-scale point clouds. So first, this is a basic definition of the task. And then the motivation of our work is that currently the existing methods, most of the existing methods, they have 2 limitations. And the first, they are limited to extremely small 3D point clouds. For example, like the point net, they usually divide their whole room into several small blocks. For example, the 1 meter by 1 meter blocks with 4,000 points. And as you can see from this figure, for this desk has been divided into 2 parts, and one is the chair, and one is the half chair, and one is half table. And another problem is that for most of the existing methods like SPG, they can process large-scale point clouds, but they either rely on time-consuming pre-processing or computationally expensive voxelization steps, so it's not practical. And then, so the objective of our method is that can we develop a method that is able to process a large-scale point clouds directly, and it should be also computationally efficient and memory efficient, and finally it should be effective and accurate. So this is an overview of our Wonderland. We found that to achieve efficient semantic segmentation of large-scale point clouds, the key problems are 2 folds. First is the efficient point sampling, and another thing is the effective local feature aggregation module. To this end, we first compare existing sampling strategies. For example, the heuristic sampling, like the farthest point sampling, inverse density importance sampling, and the random point sampling. And then we compare the learning-based sampling strategy. For example, the generator-based sampling and the continuous relaxation-based sampling, and also the policy gradients. So for more details, please refer to our paper, and you can see the detailed comparison of existing sampling approaches. So a short summary is here. We found that for large-scale point clouds, FPS and IGIS and the GIS are 2 computationally expensive. And random sampling is by far the most suitable approach to process large-scale point clouds in terms of efficiency. But the new question is here, if we use random sampling, so how can we preserve useful features? Because random sampling gives each point the same probability. Maybe some useful features will be discarded. So to this end, we propose a powerful local feature aggregation module to learn the local geometry patterns and to preserve the geometric informations. And it mainly consists of the three components. First is the local spatial encoding and also attentive pooling, and finally the dilated residual block. So for the input point cloud, we first use a k-nearest neighbor search to find neighbors for each point, and then we just explicitly encode the point positions and also the relative point positions and also the equivalent distance. And then we augment the raw features with this, like the spatial encoding feature. And then we use attentive pooling instead of use the max pooling or average pooling, which is widely used in like the computation area, because we think that attentive pooling can let the network to automatically learn the important features instead of like the max pooling, where the majority of the information has been discarded. And then of the network. Okay, and then this is the framework of our network. We follow the widely used encoder-decoder architecture with the skip connection, and we use 4 encoding and decoding layers with 3 fully connected layers. So for the experiment, we first evaluate the efficiency of the random sampling, and we found that by increase the number of points from 1,000 to 1 million points, random sampling always keep superior efficiency and memory efficiency. And here is the result of our RenderNet on the semantic kitty dataset. We found that it takes less than 200 seconds to process the whole sequence of the semantic kitty dataset. It is like 4,000 scans, and as you can see, our RenderNet also can process like 1 million points at a single pass. And then we show the results on the semantic 3D dataset, and we found that our RenderNet achieves the state-of-the-art performance, including the mean IOU performance and also the overall accuracy. And then is the result on semantic kitty dataset. Our RenderNet also achieves superior performance on this dataset. And then is the Stanford S3DIS dataset. This is an indoor 3D point cloud dataset, and we also achieve a comparable performance. Here is the result on the Toronto 3D dataset. And then we show the qualitative results of our RenderNet on the S3DIS dataset. As you can see, different color means different semantic categories. We can see our RenderNet can achieve consistent segmentation performance. And then is the result on the semantic 3D dataset. This is an outdoor LiDAR dataset, and our RenderNet also achieve consistent segmentation performance. Finally, this is the result achieved in semantic kitty dataset, and this is the most challenging dataset because the point cloud acquired by LiDAR sensor is quite sparse, and there are more than 19 categories. So, but as you can see, our RenderNet can still achieve a very satisfactory results. So to summarize, the contribution of our work is that we introduce a computationally and memory efficient network for large-scale point cloud segmentation. And then we identify random sampling as a suitable component for efficient learning on large-scale point clouds. And finally, we conducted several experiments on large-scale point cloud dataset. and to demonstrate the high efficiency, scalability, and the robustness of our approach. So finally, I will also have a brief introduction to our latest paper, that is the SensatUrban dataset. And this is urban-scale photogrammetric point cloud dataset. Each consists of two UK cities and covering about six square kilometers of the city landscape. And each point is manually labeled as one of the 30 semantic categories, such as ground, vegetation, and car. And here is some figures from our dataset, and also the class distribution, and also how we collect the data. And we also want to just hold a competition based on the dataset. So if you are interested in this area, so please stay tuned our website and our homepage to see the updates. And we also just have a roughly evaluation of the existing methods. As you can see, there is a large gap between the urban scale dataset and also the semantic 3D or semantic KT, like a relative small scale dataset. So finally, so if you are interested in our work, please follow us on our GitHub page. And if you have any questions, so we have a short Q&A stage. So, okay.
Excellent. Thank you very much, Qingyong, and of course, Dr. Boyang as well, for very quite detailed and very technical at points presentation. I have a question, if I may, and perhaps you may want to answer it together or individually. With the photogrammetric relationship to the semantic segmentation that you described, where would you say is the greatest urban application for this research today? Would it be specifically in the urban environment for urban planning, or would you see other opportunities as well, or would you imagine another vertical space that these patterns or these techniques could be applied?
Yeah, that's a great question. We also, when we release a data set, we are also receive many emails, about this data set. There are, in general, there are very exciting applications that, as far as I can, come up with. The first one, this data set is, is made from like a photometric techniques, and it's able to, kind of have a, let's say, digital city, like a digital twin. That's the technique word is digital twin. So it's able to give like detailed information for like city scale, like management, optimization, the operation related applications. I mean, in terms of the city level management. For example, we know, okay, where is the buildings and where is the roads or other related information. That's one of the important application sets, right? Another one is, we believe that in the future, like we not only have like ground robots, we could have flying robots, like air robots, In that case, that robots may not be like fly very high, it's like kind of just up in our city. In that case, we need the robots to understand what is below, So of course, we believe that this kind of applications are beyond like 10 or 20 years away. So, but now we go one step further. That's another application, but of course there are some other applications like gaming. Sometimes we have the gaming. Okay, we just have like a digital virtual city, right? Like when we play the computer games, it's made by the expert. It's a virtual city. But in the future, it's very possible that we play games like seems like in a real city, right? Yeah. Like in a city like Hong Kong or whatever, London, or but it looks amazing. But of course, in that direction, we need a map, digital map with, of course, with all the semantic information available, and then the game players are very it's very immersive. Of course, there may be many other applications. Yeah.
Yeah, very good, very good. In fact, you remind me of a quote from someone recently that urban and 3D living is already virtualized, and we're just living the offline version of those realities, that we've already crossed the line into these artificial realities. Great response, Bo. I have another question. Thanks, Alexander. Could you tell us how BowNet and Randla could complement each other? I.e., how could they be used together? And yes, yeah, in less than a minute, we've got one more minute, maybe time for one more question then.
Yeah, this is a very, very good question, to be honest. Now the RandLet deal with the feature extracting from large scale data sets, large scale point clouds. Our BowNet deal with how we learn the bounding boxes and also the the masks, so we can stack them together without any costs.
Yes.
Just it's like we use ResLet to extract features, and use the fast RSN or mask RSN to detect the segment. That's very similar.
Okay.
Yeah, and
one
also
is backbone, and another one.
Okay, so also actually we are working with that to just incorporate the 3D BowNet and the RenderNet. And the aim is to achieve the panoptic segmentation on 3D point clouds. And we are working on this. Maybe in the next year, we will release our paper. And maybe at that time, you can see how we just combine these two networks. Yeah.
Okay, excellent. Thanks very much. And we look forward to more on the paper then, Qingyong, in due course. Thanks very much to Qingyong, and also to Bo Yang. Both of you are in Oxford today, I understand. So I hope all is well over there. Thank you very much.
Thank you.
Thank you.